everybody. Welcome back to our contributed talks. Right now is the turn of Mauricio Suárez and Pedro Sánchez Gómez from the Complutense University of Madrid, Spain. And they are going to be talking about reactivity in chemistry, a propensity view. So, Mauricio, it is a pleasure to have you here. We are going to have a talk of 20 minutes. After you have spoken for 10, I'm going to let you know that you have 10 remaining minutes. Is that okay?
Yes, okay, good. So I'm actually going to rush through a little bit of this because we were interested in getting quite a bit of feedback from you. To be honest, this is quite a tentative project and definitely work in progress. We thought we'd take the opportunity of being able to present here to run some preliminary and tentative ideas that we would like to we're going to be working on during the next few weeks and months, and we're putting together for the first time. So I'm a philosopher of probability. Pedro is a quantum chemist, and so we got talking about our different interests, and we thought there may be ways of matching up. And this is a first attempt to see how that works. So can I see now? I don't seem to be able to get. Can you see the next page?
No, it moved.
Yes, it's moving now. It stopped moving for a bit. Okay, so there hasn't been a lot of well, maybe I should say there has been no mention of probability so far in the conference. And this may be striking, right? Since physics is full of probabilities all over the place, and whether emergentism is true or not, you expect probabilities to appear at different places in both chemical theory and chemical practice. So what we're doing here is we're applying ideas from the philosophy of probability and trying to find a nice, hospitable way of putting them to work in chemistry. And so first of all, I have to tell you a little bit about the framework in the philosophy of probability that we're going to be using. This is something that I've been working on for a very long time, and I've come up with something called the complex nexus of chance, which is an account of objective probability. And I'm afraid I'm going to have to be really schematic about this, but there are many publications where you find all the details of both the philosophical and technical details of this discussion, and how I came up with this view. So that will be the first two sections. In the third section, it's mainly down to Pedro. I'll very quickly present some of his work in this connection and in relation to Lewis structures and reactivity. So our claim is going to be that some of these ideas have an application to chemical reactivity, and that's what the conclusions will be all about. So I mentioned this has been work in progress, ongoing work on the philosophy of probability for a long time. I published a book with Cambridge University Press 2 years ago, where you find basically the most up-to-date version of what I'm going to very quickly summarize for you here. But all those ideas have an origin in the philosophy of physics. I came up with that framework in studying quantum probability, and so the origins of those ideas really go back to this 2010 book that I edited on causes, propensities, and probabilities in physics. Incidentally, a lot of my ideas in this field have been very influenced by Paul Humphreys. I think it was Eric who put up the photograph. He very sadly passed away just a few days ago. We're all quite shocked. He was very young. And so he was very prominent in all my development of these ideas. So anyway, the main message that I'd like to pass on about this approach is that it's approach that an attempt to change the focus of what has been traditionally the philosophy of probability. So typically, philosophers have thought of the philosophy of probability as an exercise in interpretation, and that's essentially driven by attempts to answer the truth-making question, or the ontological question, if you want, about what is it that makes probability statements true. And this is all probability statements, as they may appear anywhere in science. I'm really here mainly talking about objective probability. There have been many different ways of answering this question. There are many different interpretations of probability that are available, and philosophers have been discussing their problems, and there are lots of critical arguments against all of those interpretations of probability, whether it be the frequent test or the propensity interpretation or the best systems account of David Lewis. They all have very severe problems. So what I've attempted to do in this work, and this is something that actually Paul Humphreys was very keen on and he was doing in his own way, is to shift the focus onto a different question, a question of a methodological kind. Since we cannot really resolve ontological questions in the abstract and most generally about all uses of probability, let's see if we can do first some progress in understanding the way in which probability appears as an explanatory practice within statistical modeling throughout science. What provides an insightful account of particular regular or probable phenomenon in terms of probabilistic descriptions. And there's a whole tradition that works different philosophical accounts of probability, not as answers to the interpretational question, not as answers to a question of ontology, which I flash in red, because like Eric yesterday, well, we're a bit dubious that these questions can be settled in full generality. There are lots of problems, as I mentioned, for every single interpretation of probability and many counterexamples. But rather, let's concentrate on methodological issues. How is it that probability gets employed or used in the practice of time? And this is an account that engages and essentially builds on pluralistic accounts of probability. I think everybody is acquainted with the idea that there are two kinds of probability. Generally, there are what we call subjective probabilities. They measure credences or states of information or belief. And then there are objective probabilities, which are the probabilities that natural scientists in particular care about. And that's a pluralism that is widely accepted. And so the complex nexus of chance is an attempt to extend that pluralism to the very notion of objective probability or chance, the one that appears in the natural sciences. And so I have mounted a defense of something I call the tripartite conception, which insists that you cannot really reduce chance to either propensities or frequencies, but you really need them both. And in fact, you have to add in what philosophers call single case probabilities, which are the probabilities for the single case. I'll explain what that means in a minute. But basically, you need the three of them. And now the exercise is to locate these three different properties in whatever statistical models of particular interesting natural phenomena we come up with. And today, we're going to be attempting to do this with some of the properties of chemical reactions. So, but just to give you some examples of what I'm talking about more generally so that you get the idea. Here are three examples that we will all roughly accept as described. If you toss a coin, it has a certain probability of falling heads or tails. There are some propensities in the coin that are supposed to explain this probability. There's something about the structure of the coin. If the coin is fair, if it has been constructed or built in a way that makes it fair, then it has a certain set of properties, physical properties that explain why is it that when you toss it, it has the same probability of falling heads or tails. A biased coin has different properties. It's probably a bent coin is typically the best example of a biased coin, and it will give you different probabilities. Then you can test this by running the experiment. You just toss the coin 100 times, 1,000 times, employ the law of large numbers in order to figure out whether you have good evidence or sufficient evidence to assess that the coin is fair, and the probability that it displaces is 1/2 heads up, 1/2 heads down. So here, this is a very simple example that already exhibits the structure that I'm talking about. The system has a number of physical or maybe chemical or maybe biological properties that generate a certain chance in a particular given setup with extreme regularity. And then we can test that chance or single case probability by running the experiment and simply collecting frequency data, frequency statistics. So in this example, you already see the distinction between propensities on the one hand, which are the properties of the system, the probabilities, which are properties of the tools of the system in a particular setup, in a particular setup that can exhibit this probability, and then the frequencies, which are obviously the probabilities of experimental runs or experimental sequences, the results or outcomes of a particular experiment. So there are three different properties, and they're all involved in making sense of objective probability. This is a kind of extended sort of pluralism that goes beyond the Ramsey-Hacking pluralism and extends it into, or injects it into, the notion of objective probability as well. So let's move on to chemistry. Can this have an application in chemistry? And our tentative conjecture today is going to be that at least in some instances and in some cases and in some areas of chemical practice, these ideas can be useful and can make sense of some of the ways in which these concepts are used. Now, we begin by making a distinction, which we sort of take, inspired by Schumer's paper, which you may have, you may know, the chemical core of chemistry. There's a rough and ready distinction there between what we could call physical chemistry, which is essentially the attempt to reduce chemical properties to ultimately the quantum mechanical properties as applied to large ensembles of atoms or molecules. And this is to be contrasted with chemical chemistry, which is the rough and ready, very informal application of rules of thumb and inferential rules in order to quickly get some results in the laboratory for all kinds of different compounds and molecules. And in our case, in particular, we're interested in reactivity, in reaction rates and reaction yield. So we distinguish these two, and then you can think of the issues of interpretation as attaching to questions relevant to physical chemistry, while the issues that we're most interested in are attached to issues of what we call chemical chemistry. Now you have to bear in mind, we employ an extremely sane or minimal conception of explanation, what's called model explanation. Alyssa Bukulich is one of the champions of this account of explanation. It's very minimal because this tells you that any essential posit in a successful model of a phenomenon that proves itself to be essential for the modeling of that phenomenon is thereby already explanatory. And we realize this is a very thin or minimal conception of explanation. There are philosophers who want much stronger conditions on explanation that we impose here. We're going to impose some really very minimal conditions on explanation. And we're going to argue that Lewis structures in chemical chemistry are explanatory in just this sense. They are incorporated as essential posits in all successful models that we have of reaction mechanisms for the observed reactivity yields of different compounds. Now, I'm going to run quickly through this, which is mainly down to Pedro's contributions to chemical chemistry, and we could discuss them further in the question time. But here, here's essentially what we're talking about. You're thinking of reactivity as a kind of process that takes you from a mixed compound into a product set of compounds. All reactions have a reaction yield, which is normally less than 1. Typically, this is explained by two different means. You may have, of course, impurities in the starting products, and if you have a material that contains such impurities, you don't just have elements A and B, but you have more in the pot, then you expect to have yields that are, of course, inferior to 1. But even if you have no impurities, they're very rare, perfect reactions that would yield exactly the stoichiometric amount of products are expected. And typically there is a loss, and the actual amount of products that are obtained is in some cases considerably less than the expected stoichiometric amounts of products. And that's because the compounds react in different manners, and that there can be different products that are the yield of this reaction. So here you may have C and D, or you may have a different product E, or a different combination of F and G and H, and there may be other that are not even taken into account in the initial theoretical description of the reaction. So for instance, you have in the case of aniline, you have the ortho electrophilic substitution, and here the cationic intermediate is stabilized, and we claim there's a connection between the stabilization of the intermediate and the likelihood of the yield, and it's stabilized through the delocalization of the charge over the amine group. If you consider the para-electrophilic substitution, here the intermediate is equivalent to that of the ortho substitution, but for the meta-electrophilic substitution, there is no stabilization at all by a charge delocalization. So basically, you're going to have a very poor yield in our account, because where there is no stabilization, you expect the likelihood of the yield to be very, very, very low. So this is indicating that there are some rough and ready probabilities in the background that are explaining this connection between stabilization and yield. So if you have, for instance, these are two examples that we've been looking at: the electrophilic aromatic substitution of methoxybenzene. The ortho products are going to give you a yield of around 30–40%. The para products give you 60 to 70%. In the electrophilic aromatic substitution of trifluoromethylbenzene, that gives you mainly meta products and very, very small yields of either para or ortho. So in all these cases, there's some sort of implicit, however imprecise or qualitative measure of probability that is doing the work. And so we want to argue that in these rough and ready explanations by means of Lewis structures, you already have at play this tripartite conception of probability, even in some of the stages or the steps are implicit. So remember, we need to locate theoretical propensities, we need to locate some sense of single case probabilities, and then we need to locate the frequency statistics. Well, these are our tentative conjectures, and here we're very much looking for getting some feedback from the audience. The theoretical propensities we take to be the underlying dispositions, which are inferentially represented by the Lewis structures themselves. And here I'm applying to this inferentialist account of the role of Lewis structures within chemical practice. The role of the chemical bond in these structures is precisely to establish the possible set of reactivity products. In terms of the probability theory, what this does is to define the sample or outcome space for any probability. So basically it tells you what the different end products of the reaction can be. That's a kind of possibility space that is defined by the Lewis structures. And it's one interesting and important role Lewis structures play in this sort of rough and ready practice of chemical chemistry. So we're approaching the chemical bond in terms of its inferential capacities within the model, as in the terms of Bokulich's model explanation. And this is something that I have just been thinking over the last couple of days. But we would like to think that this is prima facie compatible with other structural or energetic view of the bond. Since it takes Lewis structures to be explanatory, and this is Robin's main request on the structuralist conception, but it also takes them to be explanatory in such a minimal sense, this of providing useful, which may be very idealized or unrealistic shortcuts to reactivity compounds, that also makes it compatible with the emergentist conception of the bond. So although we're very much starting from the practice, and we claim we should start from the practice rather than from any metaphysical conception of the chemical bond, the claim is if you just run a sufficiently minimal a kind of explanation, then you could somehow see how these two could be made compatible, and some of them may be more useful in some contexts or others. Maybe, as Eric was pointing out, the energetic conception of the bond is more useful in the case of physical chemistry. The structural conception is more useful in the case of chemical chemistry. But this is where you're going to locate this kind of set of dispositional properties. They're given to you by the Lewis structures. In fact, the Lewis structures are incredibly informative about how the different elements can combine and what the bonding can be. Well, the single case probabilities, these are harder to locate. And here, the problem is that often in chemical chemistry, you don't have a well-defined set of precise theoretical properties probabilities coming out of the stoichiometric description. So they're in principle given only with sufficient precision by the underlying quantum mechanical description. And this you can presume to exist, but it's rarely ever given, as Pedro has been emphasizing during these last 2 days, never mind solved for the sorts of chemical reactivity processes that we're looking into. So instead, what we really obtain in the practice of applying these structures is a sort of qualitative ordering of the likelihoods of the product in each reaction. So it gives you a sense in which, for instance, in methoxybenzene, the para products are twice as likely as the ortho product, but it doesn't give you anything that's more precise than that. Similarly, for triafluoromethylbenzene, as I showed you, the meta products are so much more likely than any other, but they're not 100% certain to obtain. And the others, the ortho and para products, are not impossible. They're not even entirely improbable or probability zero. So these are very imprecise or qualitative measures, but we'd like to argue they're measures of underlying probabilities, which you can get through this chemical chemist practice. And finally, the empirical frequencies, of course, these are very easy to locate. This is just what comes out of laboratory reactions, and what people actually do run the reactions and find out the amounts that result in each given case. The amounts may differ, and you can run the statistics, of course, over those amounts in order to create some sort of a statistical model of the phenomenon, which is something that happens all over the place in many areas of science, and in no way is it unique to chemistry. So we claim this is very easy to find. So you have this tripartite distinction at work. On the one hand, you have the underlying dispositional properties described by the Lewis structures, and you have the imprecisely and only qualitatively given probabilities that come out of the descriptions of the reaction mechanism. And then you have just the empirical collection of data in laboratory, which results in the empirical frequencies. So the conclusion is that we think this is fertile ground for the application of probabilistic ideas, and in particular for this complex nexus of chance. Seems that the practice of using Lewis structures explanatorily in order to account for reactivity can be rendered inferentially. And if you do that, it seems neutral. This is another bonus. It seems neutral as regards the nature of the chemical bond. You don't have to commit yourself to any particular view of the bond. You're just interested in how the Lewis structures are used in order to generate results, rather than what they refer to. And the probabilities used in this chemical chemistry practice are imprecise or qualitatively, and this just reflects the nature of the approximations that are prevalent in the Lewis structures. The more precise probabilities, if you really were after the more precise underlying single case probabilities, you really will have to give the full quantum mechanical description. And of course, they would fall out automatically out of the calculation of the square of the module of the amplitude. But its application to chemical reactivities, as Pedro has been emphasizing, is really still limited at present. So anyway, we claim these distinctions can be well articulated within this complex nexus chance of objective probability, and this allows you to understand the practice better. And also it allows you to understand the way in which probability may figure in this practice, even if it's rather implicitly and as a kind of imprecise set of probabilities or qualitative measure of probability. And that's all. We would be really delighted to get any feedback or any comments or suggestions. Thanks very much.